What?
Should I call Joe?
What?
Should I call Joe now?
Sure. Well, we know where he is, right? He's cleaning up from the robotics thing.
No, this is time. Imagine if he just doesn't come back.
I put it on speaker.
Okay. See if he picks up. Is he going to see it though? Dean and Gavin, we're calling.
Oh.
Joe, you good?
Joe, go back. I'm sorry.
Congratulations. Go back. Oh, he was trying to call you, so then we were all excited that you would pick up. Feel love. Feel love. Let him sit down. You guys. We'll grab a seat. You're fine. There's literally like 2 seconds ago. Section 10.1, Power Series. Some of you asked me, what is the point of convergence and divergence? And do you remember what I heard back from my kid in grad school at UCI? Basically computer programming, and in computer programming, Taylor series. And actually Taylor series outside of computer programming too. But approximation techniques. What have we used thus far in calculus between last year and this year to approximate the calculus? Riemann sums, okay. Why are Riemann sums useful? Riemann sums approximate area. Area approximates definite integrals. Definite integrals to be solved by hand need to be able to be anti-derived. Riemann sums uses the integrand, and you don't need an antiderivative. But you do need at least so many intervals in order to get a certain degree of accuracy. Say what?
Data points instead of the actual function.
Oh, yeah, Lorenzo's reminding us we can be given a table instead of, but we need function values, regardless, right? So a Riemann sum says, I'll take what you give me and I'll use it. I don't actually have to do the calculus, but it'll be approximate. But if you use a computer, can't it do a pretty dang good approximation so that within a certain number of decimals, like you're basically the same answer as far as like the actual value? What else do we use to approximate? Linear approximation using tangent lines. So linear approximation, we use a derivative and a tangent line, but we use the derivative at a point that we know to approximate a point that we don't know. Is that always a great approximation? No, because if you are so far removed, remember how the tangent line diverges from a curve. You're welcome. Wait, but what makes tangent lines even better? A tangent line with a tangent line with a tangent line with a tangent line? Euler's method. Euler's method says you're not stuck to one tangent line. You can do lots of tangent lines. Ooh, okay. So we have Riemann sums. The more subintervals you have, the better the approximation. Computers can go all the way there, at least close enough to be within like a 0.0000, whatever, more than we need. Euler's method says not just one tangent line, but lots of tangent lines, getting even better. What's the only other thing to do with estimation that we have besides Riemann sums and tangent lines and aka Euler's method? The one we just did. And what was that? Alternating series estimation remainder theorem. That some of you didn't do so well on Thursday and should be paying attention. Because that error thing with alternating series is kind of tricky, and it was a thing like last Thursday. Anyway, so that's an estimation thing too, right? Power series are technically way more effective than a lot of the ones that we've already seen for complicated functions. And why am I saying complicated functions? Riemann sums say, I don't need to know the antiderivative. Oh, wait, sometimes we can't find the antiderivative. And I haven't been giving you guys impossible antiderivatives because we've only been solving by hand. Or with our calculator, we're not really caring. We're allowed to use our calculator. Who knows if we can solve it by hand or not? We don't care. But power series, well, this whole chapter basically makes convergence and divergence applicable, but I'm curious as to whether or not you'll see it, especially with the question that you asked and the answer that was given. So, here we go. We're supposed to go back to geoseries. for the introduction of power series. Now, power series, Lagrange, error-bound, just like Lagrange. Maclaurens, you guys have a little bit of an accent when you talk about them. Maclaurens, Taylor Maclaurens. Sounds kind of like the Romeo and Juliet. Who were the two houses?
Montague and Capulet.
Thank you. Sounds like that, but it's not like that at all. Anyway, Taylor Maclaurens, they're actually like, Taylors are kind of like MVT, and Maclaurens are kind of like Rolle's theorem, meaning Taylors are like the overarching, Maclaurens are the special case. Anyway, this is just an introduction to all that, and we'll see if I can blow your minds just a little bit today. Okay, going back to geoseries. It looks like something so familiar, hopefully, sort of, kind of, maybe. What's the difference? Ooh, that's subtraction. What's the quotient? What's the ratio between each of these terms? R times R times R times X. Got it. When do geoseries converge?
R is less than 1.
And why am I saying absolute value of R and not just R? If R was less than 1, it could be negative 100. That's a divergent geoseries. I need R to be within negative 1 to 1, right? And then diverges if R is greater than or equal to 1. So outside, equal to 1 or beyond, equal to negative 1 or beyond. But what's the blank that's missing?
Over 1.
The sum of the infinite geometric series, if it converges, is the first term over 1 minus the R. What am I telling you to do down here? This is curious. What happens if we replace R with X? A function? No. Series aren't functions. We have to rewrite series to become functions, don't we? Wouldn't this be A plus, what if we multiply by X? Plus, is that an infinite polynomial? Is an infinite polynomial with the exact same coefficient, will it just be a geoseries? I wonder if that has any meaning. So, there we go. Technically, from like a big packet, I could have copied off and I could have given to you. All right, let's do some exploratory work with it without actually having it in your hands. What do you guys see? Quick review: geoseries multiplied by common ratio. Starting with 2 and 3, what geoseries would you write? Ready, set, go. What would be the sum of each case? Start writing your geoseries. First term, second term, third term. A1 plus A2 plus A3 plus dot dot dot. A sub n. You can even do equals and then infinite sigma, an infinite series. But what would the sum be? I'm going to do it in just a second, just giving you a head start. But then the second makes it oh so interesting. If you tend to be interested sort of person, or cool math. Someone playing something? I hear talking. Am I crazy? Can you guys just check your phones real quick and make sure something isn't awkwardly talking? Nothing else, it could waste your data. I'm doing n-1 because it started off being positive. And then I have a sub 1 times r to the, oh wait, that has a negative. Ha-ha. If that has a negative, then let's not stress. Let's just make that. Ooh, it's an alternating series too. How's that? Good? From I equals 1, or I could say n equals 1, sorry. I don't know why I went to old school I notation. N equals 1 to infinity of 2 times negative 3 to n minus 1. I think that's good, yeah? So what's the sum What does this whole thing equal?
Plus
It diverges. Why? Bummer, right? How about the first one? We actually kind of missed that one. Sorry, my bad. We have 2 plus. Now it's just everything positive. And I don't even think we need to go to the nth term, etc. I think we can just go straight here. All that's going to be different is we have a positive 3 instead. But what's the sum in this case? Also divergent, right? Because we know r, and r is outside that boundary of -1 to 1. But what about when we come down to this guy? What's my first term? What's my next term? What's my next term? What can I write as my sigma? N equals x to the n minus 1, where n is 1 to infinity. But can I say that this diverges? No. Sometimes. When does this diverge? Diverges when x is greater than or equal to 1. But what is it going to do when x is not greater than or equal to 1? To 0? Think. What will it converge to? So for certain regions, for all x's in between -1 to 1, a rational function can be written as a polynomial. Power series. A rational function can be written as. Am I the one that's playing? Oh no, Lindsay, you mean like what you're thinking about from the book? Yeah. Yeah.
I picked them outside.
Maybe it is from outside. I ain't killing it a little bit. You guys know it's not you, right?
Yeah. Oh, yeah.
Across the hallway they're watching something. Okay. Okay. Hold on. What's the point? Sometimes, for certain intervals, a rational function can be written as a polynomial, which might not really seem to be all that amazing until we say something like, okay, well, what if we had something like 1 over 1 minus x to the 5th? For x to the 5th less than 1. Could I plug in an x to the 5th anytime I see an x? Why would it be so amazing to have a rational function be written as a polynomial? Can you integrate 1 over 1 minus x to the 5th? It's not arctangent because it's not 1 plus. And even if it was, I don't have a u prime to help me out with x to the 5 halves. U sub 1 over u trying to get to ln, u sub, but I don't have a 5x to the 4th. Integration by parts only helps me if I have separate multiplications or divisions I need to deal with separately. How do you integrate 1 over 1 minus x to the 5th? I could try to factor it, so I could do 1 minus x to the 5 halves and 1 plus x to the 5 halves. How nice is that partial fraction going to be? It's not linear, so I can't just do a over b over, can't do the factor. It's not even a quadratic, so how could I make an improper or a proper fraction? Like literally, I'm thinking of partial fractions. I'm not sure you can do partial fractions. Trig sub, if we think of a 1 minus. The dilemma is trig sub has a square root, but we could try possibly. Trig sub is the one thing we could try. But then we would have the u, or the opposite side of our right triangle, being x to the 5 halves, which once again we would have a du, which would be 5 halves x to the 3 halves. I'm not sure how we'd substitute, but possibly. It would get gross. But pause. We just thought maybe trig sub. But nasty trig sub. With like fractional powers. And extra pieces. Or, instead of having to integrate 1 over 1 minus x to the 5th, what if we just had to integrate 1 plus x to the 5th plus x to the 10th plus x to the... I can do that! It's a polynomial! It's lots of power rules. Now, is it going to be good for all real numbers? No, but we could change where our 1 over 1 minus x to the 5th is centered. Like a tangent line, we can go somewhere else to where we would need to approximate it and make the power series there, and then it would be very precise. We would just need to get within 1 of the actual. So if we wanted to figure it out like somewhere between a region or at a region, integration isn't really at a region. Derivatives are though. But integration, we would need to get closer to the region in order to have the convergence be where we want it to be. Now, I'm just getting you thinking ahead. We're not even close to doing what I just said. But the idea is a polynomial I can derive quickly. I can integrate quickly. I can work with quickly. Whereas rational functions, well, sometimes they're going to be impossible. And I'm saying sometimes because there is the possibility in this case for possibly trig sub working, but there are rational functions that cannot be. And if we start throwing in things like cosine or sine, well, I don't know if we want to go trig sub when we already have trig. Just the idea, a rational function can be written as a polynomial. However, as we just talked about, well, this is still limited in that this doesn't work for all real numbers. There is still a certain convergence for this one. For this one that's built on a geoseries. Try to get it all on this. There you go, all on the screen. This doesn't work for all real numbers. But I just mentioned that idea of how maybe we could center it somewhere else. For right now, though, let's go ahead and bring in that reminder from geoseries. This only works for, or only converges for, absolute value of x less than 1 or x between negative 1 to 1. Or you can use interval notation if you want to, negative 1 to 1 with parentheses. Why am I saying explore with grapher? Well, I'm going to go ahead and put this off to the side. Some of you guys are still writing. Don't worry, it's not an Endeavor card yet. The Endeavor card has a few more than just this. Oh, stink. Can I get it there? I can kind of get it there. Can you guys see it? There you go. How do we explore with our grapher? Well, we think about the function 1 over x. Okay, the function, oops, 1 over x. There we go. Sorry, 1 over 1 minus x. My bad. I just said 1 over 1 minus r. Okay, so then we can go ahead and say, okay, 1. That's great. I mean, that's only a first partial sum. Then we could do 1 plus x. I mean, that's a little bit cooler. We could do 1 plus x squared. Remember, a series, every time you have the next partial sum, you just add on the next one. Now, wait a minute. Okay, this is starting to get really tedious. Can't we just do something like, oh, hey, it's going to be y4 plus what next? See it? Let's be snazzy, huh? And then we could do, oh, it's just going to be y5 plus, okay, we can be snazzy, yeah. Okay, let's see what happens when we try to graph this. Oh, awkward, awkward, awkward. It's all graphing at once. Nasty. Do you guys know there's a mode that lets you, instead of doing it all at once, it goes one at a time? This might be your natural one. I'm not entirely sure. Oops, sorry, wrong way. Huh. 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 Do you see it? Do you see it? I mean, this is the entire 1 over x. Now, question, does this line then parabola, then cubic, then cortex. Is it getting closer and closer to the whole function? No. But is it getting closer and closer to a certain region? Yes. And if we can make this happen elsewhere, we can possibly get better and better and better approximations without using Euler's method, but instead using curves. So if I were to zoom in, boop, bum, 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 bum. You see it? We can keep on going, keep on going, keep on going. Now guys, right now, if I were to change my window to be the negative 1 to 1, is it still diverging away? Yes, like it diverges, right? And it diverges less, and it diverges less. What does the infinite sum converge to? The actual function with no divergence. A tangent line says, I'm good there, and then I start to go off right away. The parabola says, I'm good for a little longer, then I start to go away. The cubic says, I'm good for a little longer, and then the cortex, I'm good for a little longer. But the infinite sum says, nope, I got you. Here you go. All using polynomial curves. Anyway, kind of snazzy, kind of cool. Let me bring this down here. But once again, only for a certain interval, right? Only for a certain interval. So what's the power series? What is it used for? It helps us represent rational functions as geoseries. It helps us represent rational functions, A1 over 1 minus R, as geoseries. And even more importantly, can I say that? Maybe I shouldn't say that. As polynomials when our R is polynomial. I should put that. Well, because if I have an x in the R spot, or an x squared in the R spot, or an x squared plus 1 in the R spot, or an x minus 5 quantity to the 5th in the R spot, it's going to be a polynomial. If I have a sine of x in the R spot, it's not polynomial anymore. Like, it's going to have trig. So, what you guys already wrote down, we did A and A and A and A. They're saying that constant can change, which makes it a bit more applicable. But this is a power series that's centered at 0. Like you guys saw, we can go from -1, we can go below 0 to above 0, but it's centered all around 0, which is why I was just able to hit zoom in. Because I was saying about 0. If it was centered somewhere else, I'd have to go zoom in at that somewhere else at x equals 5, or x equals 10, or x equals 11.5. I can have it centered somewhere else. I can have it converging somewhere else if I shift it. And how do we shift in math? X minus, right? Horizontal shift. We can shift it to go be convergent somewhere else that we need it to converge. Which technically we do with tangent lines too. Don't we have x minus x1? We shift them to where we want them to be. We can do that with our power series too. Now, up above, it can be useful for one application. I'm not even pretending to know all of them, but one application is representing rational functions in terms of geoseries. But what is the power series? The power series is just basically an infinite polynomial of the form that you see down below, with either 0 as its center or another term as its center. What did I just hear? Hit something over here.
Is this a never part?
Not yet. Yes. We are going to have series in our endeavor cards, and they are going to come from chapter 10, but not yet. Actually, this one might be helpful, but we don't really get to start playing with these until a little bit later. Manipulating geoseries. So not yet. Well, I should probably ponder it. We do have plenty of endeavor cards. Maybe I should make a general power series. We have a Taylor one. We have a McLaren one. Okay, you guys ready? The next example is trick B. I want you to write the function 1 over 1 minus x. The rational function, 1 over 1 minus x. And I want you to do a long division with it. You should be unhappy with that because we only do long division with what kinds of fractions? When the degree of the top is or equal to. You should also divide when they're equal because you can get like a 1 or a constant and then everything's easier. This was like partial fractions-ish, but it's just in general with integration too. Improper fractions, the top is greater than or equal to, always divide, no matter how many terms it does or doesn't have. But what's not true with 1 over 1 minus x? It's not improper. So why would we divide? Because we can't divide, right? You do long division. Don't worry about Taylor's rule. We don't know that yet. Manipulated zero series we actually just talked about. But long division. Why is it long? You're about to see. How do we do long division? You see it? How do we do long division if it doesn't go in?
What?
You don't look at this not going in. You look at how many times this goes in. I could have taught you this in pre-cal, algebra 2, algebra 1. Okay, maybe not. Algebra 2? Maybe not. Why is it long division? How long is it going to go on for? Forever. The interval of convergence without the ratio test. You can do an interval of convergence with the ratio test? We haven't learned that yet. That's so funny. But the ratio test does have a certain interval. Well, I shouldn't. We'll get there. Right now, crossing out what we can't do yet. We haven't learned Taylor's rule yet. But that long division thing. Kind of nifty. So what if I was to change it a little bit? We're playing a little bit with what's to come. We're playing a little bit. What if I was to say find a power series for 1 over 1 plus x? I'm turning this way. Aw, she can bet.
Someone's at my door.
Abby.
Coming back. How? Can we do long division? No. Why not? We could. We just did, right? You can do long division even if it's an improper fraction to get a series, an infinite series. Do you want to do long division? I'm not sure. Is there another way? Yes, but only if you look at it from the lens of, sounds like a Christian worldview class, or an apologetics class. Only if you look at it from the lens of, wait a minute, we know how to do this guy, because this guy says first term, next term, next term. Oops, I can't even multiply by x. Sorry, next term. Why? Well, it's easy. My first term is 1 and my r is x. No big deal. Got him. Check. But this doesn't look like that. Right? I can make it look like that. What's my a sub 1 this time? Still 1. Because isn't it a sub 1 over 1 minus r? Still 1. But what's my r? Oh my goodness, so we can have a 2 over or a 5 over or an x. Ooh, what would we do with an x over? Hold on. Make your series. What's your a sub 1? 1. What comes next? Oh, that's easy. Look, it's a whole, and we could be super snazzy and make it like an infinite sum and say, yay. There we go, and then we just have our a sub 1 times r to the n minus 1. What about this guy, though? Trying to fit it, yeah. Trying to make it look like. We could do long division. Yeah, we could do that all the time. Or, my long division people, wouldn't 1 go into x times? And then figure out the end then. For the rest of us, can we make it look like that? Sure we can. You can do it that way, or if you want to be snazzy, y'all just do it this way, where my a sub 1 is. What'd you say? My first term is just x, and then what's my r? So what's my first term? Multiply by negative x. Okay. Multiply by negative x. Okay. Multiply by. So what would my infinite sum be? You can either go from 0 to infinity and just say, oh, hey, it's still my negative x to the n. Or you could go from 1 to infinity and just change it to be, oops, nope, that's not good. I don't know why you would do that. It doesn't really help at all, does it? Sorry. Forget that one. I mean, he's right. He just doesn't really make anything simple. There we go. Aww. It's just that's what we have to do. We have to have the alternator be separate from the x, because the x's power does not line up with x to the 1, doesn't line up with negative 1 to the 1. I need negative 1 to be squared. We could do x times negative x. You want to do the a sub 1 times r to them? Yeah. So I'm just saying, or we can follow that a sub 1. Okay, now technically there's a lot more coming with this sort of plane. The idea is that we can keep playing and just be like, hey, it fits kind of within the a sub 1 over 1 minus r. But there's still this idea of, wait a minute, interval of convergence. Hold on. Were we even thinking about intervals of convergence when we started playing with all this stuff over here? What's every geoseries built on as far as its interval of convergence? So what changes if all of a sudden I have my r being something other than just x? If I was looking at this specific example, what would my interval of convergence become? Depending on what you plug in, it is going to kind of change or not manipulate, but affect. It's going to influence the interval of convergence, because depending on what you plug in, it might converge elsewhere. But that's actually helpful if we want it to move, like x minus 3, for instance. Well, all of a sudden, x minus 3 has to be less than 1. Oh, hey, my interval of convergence will shift. Anyway, we're going to play more. Oh, there's it forever. Oh, I mean, your endeavor. Oh, my God. Anyway, going back to this tomorrow, if you guys want to take a picture of this on the way out, if you want to start homework tonight, might be helpful. But, woo, that's a fun hour series. Yeah. If you guys want a brownie by the end of the day, come back. Thanks, John. If you did.